Okay, so we are in chapter 5. What? Who's booing chapter 5? Yeah, right. So yeah, we did exponential. No, we didn't do exponential. We did the inverse stuff last week. That was fun. What are we doing this week? We're definitely going to start exponentials. We're going to get into logarithms. Just checking your syllabus. So yeah, we're doing good. Okay, so basically section 5.2, introducing an exponential function. And the exponential function is a function of the form, basically here's the definition, f of x equals a to the power x, where a is just some real number and x is your variable. Few conditions on a is positive, because if we allow a to be negative, it gets really weird. And a is not equal to 1, because if a does equal to 1, then it's just always 1. Nothing changes. So a is called a base, and x is our exponent. And so yeah, that's a nice little function. The thing about exponential functions is they grow really, really fast. A classic example of an exponential function would be something like this. 2 to the power x. Base is 2, variable is x. And if you're going to try to sketch a graph of this thing, just plugging some x's and producing some y values. Think about this. Are there any limits on the values of x that I can use? Meaning, what do you think the domain of this function is? Is there any illegal value for x? Well, can x be positive? Can I raise 2 to a positive power? How about negative? Can x be negative? Can I raise 2 to a negative power? What do negative powers do? Yeah, it takes a reciprocal, fractional powers. Well, those are your square roots and stuff. Yeah, 0. So it looks like I can do whatever I want to do. I can do any value for x. So take negative 3, negative 2, negative 1, 0, 1, 2, 3. I'll do the easy ones from this end. So 2 cubed is 8. 2 to the power 2 is 4. 2 to the power 1 is 2, right? What is 2 to the power 0? 1. 2 to the power negative 1 is 1/2, so it starts taking reciprocals. 2 to the power negative 2 is 1/4. And 2 to the power negative 3 is 1/8. So I can grab this. Right, just plotting this point. Here's my y-intercept. 1, 2, 2, 4, 3, whatever the 8 is. And then the other one's 1/2, 1/4, and 1/8. So it gets really close to the x-axis. And then kind of shoots out that way. I don't need to go that far. I mean, you got the idea. So it's pretty low on the left. Doesn't touch the x-axis. I can never make it 0. If I try to solve this equation, it will not work. No matter how hard I try, I can get it as close as I want to 0 by making some large negative numbers in that exponent, but it will never work. So it doesn't touch the x-axis, so the x-axis acts like a horizontal asymptote on that end. It gets as close as you want to that x-axis, but doesn't quite touch it, while it really spikes up on the right, okay? And it's really growing fast. If you just, don't write this down, but if you compare this function to something that looks sort of similar, if I just compare it to the x squared function, and it just reverse the order. So if I plug the similar numbers, you know, like g of 1 is 1, g of 2 is 4, g of 3 is 9, so these values are pretty close to these values, right? They're in the same neighborhood as far as the numericals go. But if I take it a little further, if I do g of 10, so it's 10 squared, that's 100, right? But if I do this one, if I compute f of 10, that's 2 to the power 10, well, that's 1024, right? So just comparing these two numbers, you already see that now there is quite a gap. It's two, these numbers come from kind of different worlds. One is 100, the other one is 1,000. And if I keep going, if I do g of 20, what is 20 squared? It's 400. But what about this one? 2 to the power 20. It's got to be something huge, isn't it? What? Yeah, so it's over a million. So definitely quite a large gap, right? That one is still hundreds, and this is 48, was it? Don't care anymore. It's a large number, right? So the exponential functions grow really, really fast. So I want to play you this short, fun video. Yeah, it's very short.
When even a small number like 2 is multiplied by itself many times, King Shahram of India was so pleased when his grand vizier Sisabendar presented him with a game of chess that he asked Bendar to name his own reward. The request was so modest that the happy king immediately complied. What the grand vizier had asked was this: that 1 grain of wheat be placed on the first square of the chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth square, and so on, doubling the amount of wheat on each succeeding square until all 64 squares were accounted for. When the king's steward had gotten to the 17th square, the table was well filled. By the 26th square, the chamber held considerable wheat, and the nervous king ordered the steward to speed up the count. When 42 squares were accounted for, the palace itself was swamped. Now fit to be tied, King Shahram learns from the court mathematician that had the process continued, the wheat required would have covered all India to a depth of over 50 feet. Incidentally, laying this many grains of wheat end to end also does something rather spectacular. They would stretch from the earth, beyond the sun, past the orbits of the planets, far out across the galaxy to the star Alpha Centauri, 4 light years away. They would then stretch back to Earth, back to Alpha Centauri, and back to the Earth again.
Yeah, well, that was fun. What? So anyways, exponential functions grow fast. They give us some pretty large numbers, and they're fun to play with. But other than that, they're very friendly. So the graph of the exponential function in general is going to look like this. So all exponential functions have a very similar shape. They have the same y-intercept, 0, 1. The domain is just all real numbers. I can take 2 to any power or whatever. What about the range? Just by looking at the graph, what is the range of this function? 0 to infinity, not including 0, right? Since it never touches the x-axis. We have a horizontal asymptote. That's the x-axis, the y equals 0, and it only works on one side. Okay? So these are the general properties of the graph of the exponential function and function itself. Is that okay? So I want to play with this function for a little bit. Here's another example. One half to the power x. It satisfies our definition. Base is 1/2, which is positive, not equal to 1. So that's an exponential function. I can still plot the points. I can come up with the x and the y values. And I'm going to take the same range, -3, -2, -1, 0, 1, 2, and 3. So if I cube it, 1/2 cubed is 1/8. 1/2 squared is 1/4. 1/2 to the power 1 is 1/2, right? 1/2 to the power 0 is 1. How about 1/2 to the negative first power? What will that be? What? 2. You just flip this. 2, 4, and 8. That's a 4. Right? The negative, again, all that negative power does, it just flips your fraction. So if I plot these values, let me go back to my graph here. If I plot these values, I get these points. What is it? -1, 2, -2, 4. So I have something like that. Actually, I should have graphed it on where I did the 2 to the x. Here we go. Right? Same points. This one, 2 to the x. That one is 1/2 to the x. Very similar graphs, right? What is the relationship between them? I mean, how can I go from one to the other as far as, maybe a symmetry of sorts, or do you notice any patterns between these two? Yeah, if I rotate one of them around the y-axis, it basically becomes the other graph, right? If I take the green one and I flip it, it should overlap the red graph. Do you agree with that? Now, when does that happen? When do we flip a graph around the y-axis? Going back to chapter, I don't know what. When we did what? Well, even functions are symmetric around the y-axis. These functions separately are not, right? But if I flip one over the y-axis, I get the other one. So in the list of your 10 transformations, when you shift left, shift right, sometimes we flipped over the x-axis, sometimes we flipped over the y-axis. When do we flip over the y-axis? That's a good review. Anyone? Where are the parentheses? So putting a negative like that? Well, yeah or maybe? I'm not going to show it. Are you going to tell me? Well, let's think about this. Remember we talked about all the transformations, right? how they relate to the variables. Well, what is the difference between these 2 points? So if I look at this point right here, -2 and 4, whatever, and this point right here, +2 and 4. What is the difference between these 2 points? Well, let me just -x, right? So we have to change the x value in order to go from one point to the other. So how do we change the x value? I mean, the sign of the x value, you just put a negative where the x is, right? So it's negative from the inside the function. So that's one of your transformations, f of -x. To sketch the graph of f of -x, you flip it over the y-axis. Well, let's see whether this thing holds. Well, if I take f of x equals 2 to the x, so that was the original graph. And if I try to compute f of -x, so it means the graph has to be flipped over the y-axis, well, that becomes 2 to the -x power, right? And what does the negative sign does in the exponent? Flips it. So that becomes 1/2 to the x. So this is another way to see that the flip, one is the other graph flipped over the y-axis. This is how you take the reciprocal. You're making an exponent negative. So there are really 2 types of graphs when you're dealing with exponential function. One is when the base is greater than 1, so things are growing. The other type of graph is when the base is less than 1, just like when you saw with the 1/2 base. So the function is declining, but the rest is the same. It has same domain, same range, same intercepts, but it's a decreasing graph. Is that okay? So I'm not going to plot any more points, but basically the idea is the bigger the base is, the steeper the graph. And that should make sense. If you raise 2 to the powers 1, 2, 3, or if you raise 3 to the powers 1, 2, 3, you're getting larger values. So we can easily see that on foo plot. If I graph 2 to the power x, and then if I graph 3 to the power x, you see what's happening? The larger the base, the steeper the graph on the positive side, but on the negative side, the larger base is below, because you're taking reciprocals with bigger denominators. So it is bigger on the right, and it's smaller on the left. Okay? So same thing holds if I actually take reciprocals of them. Same kind of scenario. Okay, so the steeper the base, the higher the graph is. Does that make sense? So all other transformations still apply. So if I ask you to sketch the graph of this function, let's say 2 to the x plus 1 plus 1, like that, all our rules of shifting things around still apply. Okay? So we will start with the graph of a function that we already know. So this is your basic 2 to the x. Right? So where does it have to shift? There are 2 things that are going to happen. If you add 1 to the variable, where is the graph going to go? Left. And you add 1 to the function, the graph is going to go up. So it has to go 1 unit to the left. Well, I cannot move it separately. But anyway, so I have to go 1 to the left and 1 up, right? So the thing is that the horizontal asymptote will go up with the function. So it will do something like this. It shifted 1 to the left and 1 up, right? We can actually find the y-intercept. How do we find the y-intercept? you set x equal to 0. So if we do that with that function, it is 2 to the power 0 plus 1 plus 1. So we get 3. So it's actually higher than I was trying to show, but it's going 1 up and 1 to the left. So the y-intercept is at 3. And again, we can sketch that 2 to the power x plus 1 plus 1 here. But it still has that gap on the left for the asymptote. The common mistake is to write it all the way down to the x-axis. It doesn't have to. It has to even out at the new horizontal asymptote because everything shifts. Okay. How's that? Is that good? Well, it's not so good. It's good, right? It's nothing weird yet. So every time we have a phenomenon that has this, well, what we call an exponential growth, is when, as you saw in that rice example, when things doubling in each term, or when things have a fixed growth rate. So that would be the population, that would be, not just human population, you have a population of bacteria, whatever you're looking at, or you have a small pile of uranium in your living room, and that thing kind of probably, hopefully, declining in the amount. So that has an exponential effect. You have some money in your bank account, maybe. It's gaining some interest, or you owe money to a bank. They're gaining some interest. So those effects that have some kind of a rate that based on the initial amount follow these types of models, okay? So I'm going to first focus on the interest examples. And we haven't played much with the interest. We had the simple interest up to this point. And the formula for the simple interest was PRT. We've used that before, where P is the principal, whatever you invest, rate is the rate, and T is the time, okay? Okay. So for example, just to make a simple case here, let's say we have, how much money do we have? $500? All right, so let's invest 500 at what rate? 2%. 2% annual rate. What? That's, well, depending on what you're doing. I mean, if you're going to walk into a bank, they won't give you that rate. They'll be like, that's really high. For how long? 2 years. Okay. Good. So can we figure out how much money we have in the end? Well, yes. So the amount of money that we have is your principal plus the interest, right? Whatever you invested plus whatever the interest is acquired. We can actually play with this formula because the interest is PRT, so I can factor the P. It's P times 1 plus RT. There's kind of a fancified version of that formula. So it just spits out the final amount in your bank account. So if I plug everything in, so let's call that the amount. It is 500 and then 1 plus 0.02 times 2, right? Rate is 2% for 2 years, so we get that. So this is 500 times 1.04, right? How much is that? $500 and Anyone? Is it 520? Are we sure? All right, good. 520. So, but that means this little scheme, or whatever you call that, is very unrealistic. Your money does not sit in your bank account for first 300, no, what is it? 729 days at 500, then on the last day they go, oh, $20. Then you got that much, right? That's what this implies. That the payment occurs at the end of this investment period. So for the first 1 year and 364 days, at any given time, it's just $500, and then it gets added those $20 or whatever, right? Okay. Well, let's say we're going to do something else. Instead of computing this interest once at the end of the whole investment period of 2 years, let's compute it at the end of each year. So we're going to compute interest at the end of the first year, added to the principal, and then we're going to compute the interest at the end of the second year, and then add it to the principal. The difference is that at the beginning of the second year, we have a little more money in our bank account because our principal is higher now. Because what I'm trying to say here is this first year, so here are the years. So here's the first year. You start with $500, right? And then the interest was what? It was that 500 times 0.02 times 1, just for 1 year, right? So at the end, the amount in the end, if we use that little fancier formula, it is 500 plus 0.02. So at the end, we have $510. That at the end of the first year. Is that okay? So at the beginning of the second year, we're going to start with that amount. So we're starting with $510 instead of 500. So then we compute our interest over higher principal. So it's $510 times 1.02. How much is that? Right? Well, that's exciting, isn't it? It's extra 20 cents that we did not have before, just because we computed an interest twice during that period, right? Well, that feels better. Did the math make sense, what I did? What if I do this at the end, so compute interest at the end of each month? So over 2 years, that's 24 computations that I'll have to do. So that's going to get a little difficult. So first year, we'll start with $500. Well, what is my rate? And this is not the year, actually. I want to do it at the end of each month. So this is M for months. So what do you think is the interest rate per month? If it's 2% for a year, what do you think, how we're going to compute the interest rate per month? 2 divided by 12. We're going to take the annual rate and divide it by number of times we're going to do this thing. So if it's monthly, we're going to divide it by 12. If I decide to go weekly, we'll divide the rate by 52. If I decide to go every second, I can do that. How many seconds are in the year? Do you guys know? So let's see, 365 days times 24 hours times 60 minutes times 60 seconds. So yeah, that many. Okay, so we can do it, yeah, whatever that number is, that many times per year. I mean, you just compute the interest at the end of each second. It's a very tiny fraction, but hey, everything counts. So for now, our rate is 2% divided by 12, so that's what? Whatever that is. It's 0.02 divided by 12. Who cares, right? So our amount is 500 times 1 plus whatever that rate is. Well, I should make it a little more friendly, right? It's 1 over 600. If I simplify that fraction, it's 2 over 1200. It reduces to 1 over 600. So whatever this is, if I compute that, equals that plus 1 equals that times 500. So 83 cents. At the end of the first month. Okay? Now, so that means at the beginning of the second month, we're going to start with that amount, and we're going to compute the interest over that amount by doing this computation. Right? So who's with me on what I'm kind of doing? How many more times do I have to do that? Yeah. 23 or 22, depending whether you consider that one done. And if I go all kinds of psycho on you and ask you to do this for every second, you might get very disappointed, right? Because we saw how many times we have to run that thing. So of course we have to start looking for a pattern. Maybe there is a quicker way of doing that. I mean, computing this every time, yeah, we can use Excel and just copy the formulas down. That's boring. Because look, the number 500.833, that's this expression, right? That's where we got 500.8333. So I can actually replace 500.833 in my second month computation with the computation from the first month times that extra interest from the second month. So this will be the interest from month 1, and this is the interest from month 2. Now these are the same expressions, so that becomes 500 times 1 plus 1 over 600 to the power 2. So that's for month 2. And do we get the same number? Kind of take a mental image of that number. And let's do it again. So it's 1 over 600 blah plus 1 equals that to the power 2 times 500. Is that the same number? Okay. So who can tell me how am I going to compute at the end of the 24th month? What do I have to do? Change the exponent to 24. So this is 500 times 1 plus 1 over 600 to the power 24. That will tell me how how much we have in our savings account or whatever that is if we compute the interest at the end of each month. So that has to be raised to the power 24. No, not yet. Let's go back. 1 over 600 equals that, plus 1 equals that, right? And then raised to the power 24, and then times 500. So what is it? 520.39? We did good, right? There's a benefit in doing that little computation thingy because you get more money, right? Because that extra interest that you started compounding on each of those intervals is compounded over a bigger initial amount. Slightly bigger, but it adds up. I mean, we're just playing with 500 over 2 years. What if we put a little more in there and for a little longer and so forth, okay? But let's break this one down, how we came up with these numbers. This number was really the interest rate divided by, well, we divided it by 12, right? By the number of months or the number of time intervals. So let's call it n. And what is 24? 24 was, well, how many total intervals? So that's the number of years, 2 times 12. So that's n times t. So this is the formula for compound interest. So that's our second case. Compound interest formula. And the formula is, so the amount at time t is given by the principal times 1 plus r over n to the power n times t. R is your annual rate, n is the number of times the interest is being compounded per year. Okay, so when we did monthly, n was 12. If we do weekly, n is 52. If we do it every second, whatever that number was. Okay? Does that make sense? So P is the principal. R is the rate. N, number of times. The interest is compounded per year. So try this one. So let's say we invest, I don't know, $1,200 at 3 3/4 rates for, I don't know, 7 years. Okay, so I want us to compute the final amount for when the interest is simple interest, to compounded annually, compounded monthly, weekly, see what kind of numbers we're going to get. Can you guys do that? Well, do it. Tell me what the numbers are. I'm going to hide the Excel in a second so you can see what we're doing. So the way you would set this up, for the simple interest, you'll just go, well, this is your formula. So you will just take 1200 times 1 plus 0.0375, because that's 3 3/4, times 7. So that's for the simple. Whatever that is, it should come out to 1550. Okay? But for the compound annually, that means n equals 1 in our formula. So it's once per year. So then the amount will be 1200, and then 1 plus the interest rate, 0.0375, raised to the power 7. So 7 times 1 is still 7. Now for the monthly, n equals 12 now. So you'll do the same thing. You'll take 1200 and then 1 plus 0.0375 divided by 12 to the power 7 times 12. Right? It's 12 times per year. Now you have to be careful with your calculators. Your calculators are silly. Make sure you put parentheses around that. Otherwise, it will raise something to the power 7 or just multiply by 12. So you have to tell your calculator what you really mean. For weekly, n equals 52. So it's 1200, 1 plus 0.0375 over 52 to the power 7 times 52. Right? So if you plug those into your calculator properly, you will get these values. Okay? Did you get those values for those of you who tried? Yeah? What? Well, you don't have a calculator. You're lying to me. You do. You're not lying to me. But did you get those numbers? Okay. So what is the trend? Is there a pattern? There's one obvious pattern. What yeah, so the higher value of n, the more money you make. Now, the other thing you realize that, well, the jump from simple to just annual is spectacular, right? I mean, that's a big jump. But then when you went from once per year to 12 times per year, yeah, you got extra $7, so, good. But then you went from monthly to weekly, that gain, the amount that you gain is starting to flatten out. So if I just bump that number to whatever the 10,000 is, well, it went up, but not that much, right? If I go higher number, okay, so it's the same thing. Seems like it's starting to flatten out. I mean, we do see, there's some difference in the decimal, so that's where the gain is starting to happen. You don't even see it anymore, right? So eventually it will even out. And that's the nature of the curve. There is an asymptote, okay? So in a way, the values start flattening out a bit, okay? Now the question is, well, what is the absolute maximum that we can earn with this scheme, 7 years, 3 1/4, $1,200, without changing any of those conditions? So the only thing that we can play with is the value of n. And you can make n as large as possible. Oh, look at that. We gained something there. I think that's actually an error already. I don't think that kind of jump should have happened. Yeah, that's more like it. So you see the Excel starting to fall apart because of the rounding errors. I mean, if I keep increasing the value of n, the change will only occur on those far decimal places. So the main part of that number will become unchanged. So there is a way to find that absolute maximum setup. And we can play with this idea. Let's invest $1 for 1 year at 100% interest rate. Okay? Okay. So that should make sense, that if you invest $1 at 100% interest rate for 1 year, at the end of the year, simple interest, you get $2 because it's 100%. Or if you compute it once per year, you still get $2, the same thing. You compound interest once, right? Now, if I start increasing the value of n, the value that we can earn starts increasing. But again, to a point, the level of increase is starting to slow down a bit, right? So if I keep going further and further and further, this part of this number, 2.718 and some junk, will not change. And that's an important number. It's an important constant for the future of this course, and depending how far in math you're going to go, you'll be seeing that constant more often than you see pi. That's your other favorite constant. There's a special name for this constant. We call this e, a lowercase e. So we're just introducing a whole new number. It's a big day. How many of you have met e before? Some of you have met e before. Okay, so new number e, new old number e. E is approximately 2.718 and blah, blah, blah. Nobody cares what e equals to. Your calculator does have e button. If you open your calculator, locate the button that looks like this, 2 letters, L and N, and look right above it. It says e to the power x, right? So if you want to compute the value of e, you have to raise e to the power 1. So on this calculator, I have to hit this button to get e to the x. So I'll hit 1, that. So here we go. So here's that number e. Your calculator does have it in it. You don't need to know what it is. Nobody cares. If I ever ask you what is e squared, you'll just plug it in your calculator. You'll go, okay, 2, yeah, here's e squared. You raise e to the power 2, and so forth. Okay, so get familiarized with your calculators how to do that, how to raise e to, or any base to any power. but that's a fancy little number. It's irrational, just like pi is. It's irrational. So that means that decimal goes on forever, pretty scholastic, and there's no pattern. Now the exponential function is f of x equals e to the x. Is that a legal thing? Yeah, e is a constant that's positive, not equal to 1, so it's an exponential function. E as a number is somewhere between 2 and 3, so the graph of it looks like that, just like any exponential function with a base greater than 1. It lies somewhere between 2 to the x and 3 to the x, closer to 3 to the x. If I use foo plot to graph 2 to the x, 3 to the x, and I don't think it does just e to the x. Oh, it does e to the x. So you see that? The e to the x is just a little closer to 3 to the x, above 2 to the x. So that all makes sense, right? Just a friendly little function. Don't be afraid of e. E is good for us, and it's good to us. But with the use of e, we can have a third, probably the most important formula for computing the interest. We call it the continuous interest. That means the interest is being compounded not fixed number of times per year, but infinitely many times per year, so continuously. At every moment, the interest is being compounded and added to the original and computed again and blah, blah. So this is the absolute, most you can get out of your investment if you don't change the terms of the investment, if you only change the number of compounding. So that's the continuous interest formula. And that's your A of t is P for principal, E for E, raised to the power RT, like that. So that's a famous PERT formula. Spells PERT. That's an important formula. We use the same formula to model population growth, population decay. We play with money as well. Anything that we can think has an exponential rate of change, we can play with that formula. Okay? So using the same conditions, if I invest $1,200 for 7 years at this rate, so I can compute my future amount. It's going to be 1,200 times e to the power 0.0375 times 7. P e to the power RT. If I plug this into my calculator, this is how I'm going to do that. I'll first compute that exponent times 7. So that's the power. Then raise e to that power, and then times by 1,200. So here we go. 15. So it didn't change much from the amounts we were getting before, right? It's still 15, 60, and 21 cents. Okay? So a lot of times when you walk into the bank with a pile of cash and you say, hey, take my pile of cash and give me the percentage. We don't know how they compute the interest. I mean, that information is rarely disclosed. I mean, you can probably ask for it. One of the reasons why it's not being shared is because, well, most people don't, understand some of those financial formulas behind it. But, if you walk into the bank and they'll give you two options. Option 1, I don't know, 4%, simple, or option 2, let's say it's 3 3/4 continues. And I'm just pulling this out of my, I don't know what. Which one is better? Because you see, like, if we don't see this information, if this information is hidden from us, then clearly, 4% looks a lot better than 3 3/4. And maybe it is. But we can compute that, right? We just pretend investing anything at all, $1, pretend investing that dollar for a year, because it doesn't matter what time it is. So if one grows faster, then it grows faster, regardless of amount of time. So if I do $1 for 1 year, then option 1 will give me what? 1 plus 0.04, right? So $1.04. That's just simple interest, right? 4% at the end of the year. But option 2 will give me e to the power of 0.0375, right? Investment is 1, time is 1. Well, if I compute that, and that amount is, again, I have no idea. I'm just guessing. Just pull 2 numbers. So just a tad smaller. So option 1 is still a better option, right? But if we change 3 3/4 to 3.9, maybe option 2 will be better, right? So they don't tell us that, but they do tell us one thing. When you walk into the bank and they give you, like, there is a list of, the certificates of deposit or whatever, and they give you 2 numbers. They give you the APR and they give you the APY. Do you guys know what I'm talking about? Have you ever paid attention to those posters or whatever? Or maybe took some kind of a business financial course? APR is the annual percentage rate. So whatever it is I was given to you here. So, whatever that means. While APY is the annual percentage yield. And that's a more important value because this number will tell you what, if you assume the simple interest, that's what the interest rate would be. Didn't make any sense. Let me explain in a second. Okay? So here's an example. So finding annual percentage yield. Okay? So let's say you invest $100 at 3.5 rate compounded, I don't know, daily. Okay? So we can, for 1 year. So we can compute how much money we have at the end of the year. So the actual amount is 100 times 1 plus 0.035 over 365 to the power 365. Okay? So I can compute that pretty easily. Just plug this into my calculator or whatever. 0.035 divided by 365 equals that. Tiny little number. Plus 1 equals that. Raised to the power 365. And then times 100. Right? So we got $103.56. Okay? You with me on that? Well, now let me ask you this question. Here's another scenario. You invested $100 for 1 year and got $103.56. The question is, what was the interest assuming that's a simple word, simple interest. So in other words, what does interest have to be in order to go from 100 to that using the simple interest formula, right? Because we know the simple interest formula, P times 1 plus RT, right? That's the simple interest formula. So for everything that we have, it is 100 times 1 plus what? Well, I don't know what rate is. Over 1 equals 103.56, right? So then solve for R. Right? If you solve for R, we'll get that. This is what we mean by annual percent yield. That's your yield. If you assume the simple interest, then none of those compounding things matter. If they tell you, yeah, the annual rate is this number, but the yield is something usually a little higher, so you just use the simple interest to compute whatever you have in the end. So that's what yield is. Does that make sense? If they just tell you APR, that's meaningless, because you don't know how they're going to compute it. But if you see what the yield is, then you just, oh, it's just simple interest, and then you know exactly what you're going to have, so you don't have to play with all those formulas. So that's a more important number, right? Because again, the way they do that makes a difference, especially on your credit cards, because the way they compound your monthly interest charge is slightly different the way they compound your savings. Could be in the same bank, but they'll make sure that, oh, anyways, you know what I'm trying to say? Yeah. Okay. So let's do this game. Let's play this game. So let's say you want to make a purchase. What do you guys want to buy? All right, well, somehow I knew that. How much does that cost? 800, okay. Not an issue. So you want to buy something that costs $800, and let's say you have enough patience to wait like, I don't know, 15 years. How about that? You're going to wait 15 years to buy that new, sweet $800. Or you want to wait less? You want to wait less? 7 years? All right, 7 years is a lot better. So you want to buy something that costs $800 in 7 years. All right. So Louis walks over to you and goes, hey, I have this, investment opportunity that pays 6 3/4 interest rate. And you're going to ask Louis, well, how are you going to compound that interest? And he goes, monthly. All right. So the investment pays 6 3/4 compounded monthly. So the question is, how much should you give Louis today? So 7 years later, you bring him, here's your $800. So how much to invest today? And we're really playing with simple formulas. There are so-called annuity formulas, because nobody saves for a snowboard like that, right? You don't just dump $600 and then you wait 7 years for it to become $800, right? More realistically, you're going to put, I don't know, $25 into your account once a month. And then think about this. If you're going to save for 7 years, $25 you're going to put today is going to earn a lot more interest than $25 you're going to put 3 years from now. So there's some fancy formulas. We can derive them. I don't think we're going to do that. It's getting a little messy. But so that's a very simplistic form of a problem. So we don't know P, right? The principal we don't know what the principal should be. But if we set this up, it's 1 times 1 plus 0.0675 divided by 12 to the power 7 times 12, right? For 7 years, monthly, n equals 12. We want this thing to be 800, right? That's the goal. So the question is how much to put in today. So 7 years later, it's $800. That's a linear equation. Do you agree with that? It's a variable times a constant equals a constant. So really, P equals 800 divided I mean, we can plug it in a calculator, hopefully. How we're going to do that? We're going to work this thing backwards. So 0.0675 divided by 12 plus 1, and then raise it to the power, whatever 7 times 12 is, which is 84-ish, to the power 84. So that's my denominator. So I'm going to flip it times 800. So $499 and 41. So basically $500. If you give Louis $500 today, he'll bring you $800 7 years from today, provided that's those are the rules of the game. Does that make sense? Okay, so we can solve this. We can work these things backwards. So P, roughly, 500. Okay. How was that? Did that make sense? We didn't have to invent anything new to answer this question, because the equation that we ended up with, that's a linear equation. We can always solve linear equations. Well, what if we change this a little bit? Let's say all you have 350 right now. You don't have 500. Well, Louis still has his 6 3/4 compounded monthly type of deal. And you still want $800. So the question is, how long to wait? How do you spell wait? E? No? Is that it? That's weird. How long to wait before the investment reaches 800 provided 6 3/4 rate compounded monthly. Slightly different situation. Okay? So the unknown variable here is t. We don't know what t is. We don't know how long to wait. The way we can set this up is $350 of your initial, whatever it is you have, times 1 plus whatever the rate is, over 12 to the power 12 times t equals 800. Right? So that's no longer a linear equation. The variable is cramped up all the way in the exponent. And we do not have any tools to solve that equation at the moment. You can probably guess that it's going to be more than 7 years, right? Because for 7 years you needed $500, you have $350. You can play the guessing game. Some of you, by the way, some of you probably know how to solve this equation. That's okay. But all you have to realize right now, with the tools that I have, the tools that you have, we cannot solve that. There's no way we can solve that. We can guess, again, you can just start plugging numbers in, see which ones work. But to get a precise solution, we're in trouble. All right? So this is kind of goes back to last week's class. If I give you a simplified form of that equation, the base is a constant. The base is a constant. The variable is in the exponent, just like here. We can solve this equation by guessing, right? That's a clear solution. What is x equal to? What? 3, right? Because 2 cubed equals 8. But if we change this one just a little bit, we don't know, right? We cannot solve that. We cannot get x by itself, right? And remember the whole Wednesday's class, we were trying to solve equations by blowing them up so the variable falls out. We were doing some tricks where you can come up with a certain function if you take composition of both sides, then the left side is automatically x, and the other side is whatever this number is. So we were playing with inverses. Remember that? That's a section 5.1. From Wednesday? You don't remember that? So what? It's all being recorded, right? Well, you missed a few classes, but you were watching this, or somebody was watching this. I see the hits. Somebody's watching those things. What? So, yeah. So let's talk about this. For those of you who were here on Wednesday. So here's our exponential function. Okay? We know that domain of this function, domain is all real numbers. The range is from 0 to infinity. We know that, right? Now, does this function have an inverse? Especially from those of you who were here on Wednesday. Does this function have an inverse? What is the necessary condition for a function to have an inverse? Well, you guys have no idea what I'm talking about. Why? Yeah, well, but I can do it to any function. I can always swap x and y. So why is this one, if I do with this function, it will actually work? I'll get something meaningful. How we know in advance? What were you trying to mime there? What was that? No. Yeah, that's the ax. No, that was the 1/2. That's those are not inverses. How do we know that a function has an inverse? Horizontal line test. That's right. The one-to-one functions, right? The one-to-one functions have inverses. So there is such thing as the horizontal line test. That's what we talked about on Wednesday. So if a function, if you do that to a function and every line crosses the graph at least, and at most one point, that function is a one-to-one, therefore it has an inverse. All right, good. So it does have an inverse. So let's talk about that inverse. We know the domain of that inverse, don't we? What is the domain of the inverse function? Given all that? Anyone? What is the relationship between 0 to infinity? Remember how the domain becomes the range, and the range becomes the domain. So that's basically a swap, right? So we know that much. If the original function has a 0.01, then the inverse function has a 0.10, right? And also, remember how to sketch a graph of the inverse function given the graph of the function? What is the operation that we did last week? Anyone? How did we sketch the graph of the inverse function given the graph of the original function? We flipped it over the line y equals x, right? So if I do that, if I visualize flipping the graph of a to the x over the line y equals x, I'll come up with something like that. So this little red graph is the inverse function, of the exponential function. Now we know everything there is to know about that function. We know the domain of that function, which is reflected in the graph, right? Just strictly positive. We know the range of that function, all real numbers. We know the graph of that function. We just don't know the name of that function, and that part is kind of not important. We all know the properties. So we decided to give a name to that function. That is the logarithmic function, and the way we write that, something like this. And I'll tell you in a second how to pronounce all that. But, you know, the name was kind of the last thing we decided to provide to this function. So this reads as log base a of x. Okay? So this little number on the bottom is kind of the same number as that base. So that's the inverse of a function, of the exponential function. Now think about this. From what we, again, discussed on Wednesday, we understand how the exponential functions work. We understand how this function operates. If I put a number for x, I'll give you an exponent. It will give me some value back, right? It will give me what you get if you raise 2 to that exponent, right? If I ask you what is 2 to the power 2 is, you'll say it's, well, it's 4. If I ask you what is 2 to the power of pi is, you know, I don't know, but that is computable. 2 to the power, where's my pi button? Pi. So whatever that is, 2 to the power pi. So given the exponent, I already forgot what it was. Given the exponent, you get some kind of an output. So the inverse function should work the other way. Given the output, it should give us the exponent back. Okay? So it will tell us to what power to raise that base to get a whole range of numbers. For example, if I ask you what is log base 2 of 8 is, the question is, to what power we need to raise 2 to get 8? So it does the opposite. Instead of 2 to the power of 3 equals 8, it does to what power to raise 2 to get 8? And the answer is, what? 3, yes. Is that okay? Anyways, go do this week's homework, because we're talking 2 different languages at the moment.